Now we look at independent events. So we say that two events, A and B, are independent in the sense that if the occurrence of one event does not affect the occurrence of another. For example, you can say, hey, the soccer game, and let's say the soccer game, the result tonight is independent on whether it will rain or not tomorrow. So this is the two things have nothing to do with each other. And in statistics, we define two events, A and B, being independent if and only if the probability of both of them occurring is equal to the product of each of the probabilities. So P of A and B equals P of A times P of B. So let me just give you an example of independent events. So let's say there are two marksmen, and the first person gets a bullseye 20% of the time, and the second person gets 40% of time. If both shoots target once, and of course we assume these two marksmen are independent, and then what is the probability of both to get bullseye? So let's do this calculation. So here we let A be the event that marksman A gets the bullseye. Marksman 1 gets a bullseye. And then B be of course, the marksman. The second one gets bullseye. And we know that these two events are independent, so we want to find the P of A and B. And this is calculated by P of A multiplied by P of B. And we know that P of A, the probability of the first person that gets the bullseye is 20%. So that is 0.2 and multiplied by P of B, which is 0.4. And be careful, this is not 0.8. Okay, this is 0.08. So the probability of both of them got a bullseye would be 8%, which is not very likely, but it could happen. And another example is one day of 4, Nancy forgot her morning chore of putting plants out in the sun. So here, A means we're going to two events. A means Nancy forgets. And B would mean B means the weather, the sky is overcast. Now, here, and so her oversight doesn't really matter. What is the chance that she forgets and that does not matter? So P of A and B. Here we assume that Nancy's forgetfulness is independent from the weather. So P of A and B is equal to P of A times P of B. So in this case, the P of A is 1/4. So it's going to be 1/4 times 1 day in 5. So that is 1/5. So which is 1/20. So this is the chance or the probability that she forgets, and it does not matter. Let's look at another slightly more complicated example. Let's look at a chair cushion. And here, suppose there's the department store, it holds a clearance sale, and you want to purchase a pair of matching cushions for an old rocking chair. There are 2 boxes of leftover cushions. So here, one box is the seat cushion. So we're going to do this box as the seat cushions, and another box is the back cushions. So this is the back. Now, in the seat cushions, there are 3 white ones and the 4 blue ones. Of course, they're all mixed up, and 1 red one. And now for the other box, there are 2 red ones and also 5 green ones. Now, we would like to draw a cushion at random from each box. So basically close your eyes and mix them up and just draw one. And what is probability that you select a white seat and with red back cushion? So here, let A be a white seat and B be a red back. Again, you can do a P of A plus A times B or A and B. Is equal to P of A, not less than equal to P of A times P of B. And the chance of drawing white seat cushion is 3 out of 7 or 3 out of 8 cushions. And then chance of drawing the back cushion is, the red back cushion is 2 out of 7. So at the end of the day, you can get 6 over 56 or 3 over 28. So that's not a very high probability, less than a little bit over 10%. And also, what is the probability that cushions are the same color? In this case, I encourage you to pause the video and spend a minute or two working on these problems. Okay, assuming you have already done that, and let's examine these boxes. So the only way to make the cushions of the same color is to choose the red one from the first box and also choose the red one from the second box, because that's the only same color from both boxes. So the chances of choosing the red one from the first box is 1 over 8, and the second one, the chance or the probability of choosing the red one from the second one is 2 over 7. So it's 1 over 8 times 2 over 7, which is 2 over 56. And, or in other words, it simplifies to 1 over 28. So that's the answer for the second question. All right, so now let's consider lemon cars and wildcat origin. So, and I hope nobody would buy a lemon car. A lemon car basically just means the cars with some defects. Suppose that 1/10 of the car are lemons, so there are problems. And also 1 out of 20 of wildcard origin are successful. If we just buy a car and also invest in a wildcard drilling adventure, what is the probability that both of our outcomes are favorable? So here we're basically doing two things. They're independent, and what car you buy has nothing to do with whether your oil drilling is successful. So if you're not careful, you might just say, I will just multiply 1/10 by 1 over 20. Well, here's the thing. The question asks, what is the probability that both outcomes are favorable? Favorable means it's good for you. It's some good thing happens, and you don't want to buy a lemon car. So here, the chances of buying a lemon car is 1/10. That implies the chance of not buying a lemon car is 9 over 10. So for this question, the answer is you should use 1 minus 1 over 10, which is 9 over 10, times 1 over 20. Now your result is about 0.045 or 4.5%. So if you just do this thing randomly, the chances of both of them be favorable is actually pretty low. And what about 2 or more independent events? And the same principle applies. If you have 3 events that are all independent, A, B, C, and for all of them to be happen, you simply multiply the probabilities together. And for the next example, I don't even need to write it on the board. And look at here. If you have a family with 3 children, what is the probability that all of them are girls? We assume that for each child, there is equal chance for the child to be a boy and a girl. So let A be the first child being a girl, and B be the second one being a girl, and C be the third one being a girl. And assuming they are independent, and then we're doing A of P of the first one being a girl, P of, and the second one, and the third one are all girls. So that's equal to the product of P of the first one being a girl, that's 1/2, times P of the second one being a girl, that's 1/2, times P of the third one being a girl, that's also 1/2. So the result is equal to 1 over 8. Okay. And now let's take a look at the next example, the Pennsylvania Late Day Lottery. All right, so like many states, there is a daily lottery. By the way, by teaching you the example, I don't mean to encourage you in any sense engaging in this lottery. To me, this is a waste of money, and this shows the greediness, and this violates some biblical principles. So I don't encourage you to do this at all. But let's just take a look at this example. And so basically, people buy the lottery tickets and try to guess this which three-digit number. So from 000 through 999, and will be picked at each evening at 7 p.m. The winning number is produced from 3 separate machines that contains 10 ping pong balls labeled 0 through 9, and they're just blown out in the container by a jet of air and mixed. So and then one is sucked through an opening at the top of the machine. So basically the setup is random. And what is the probability the number drawn on any given day will be 1, 2, 3? Well, the chance is, well, here the first digit being 1, the second digit being 2, the third digit being 3. Well, those three events are supposed to be independent. The probability of getting the first digit being a 1 is 1 out of 10. It's 1 over 10. Well, the second digit being 2, and some of you say, is that 2 over 10? No, it's not 2 over 10. 2 is just a number, one number. So the probability of the second number being 2 is still 1 over 10. And the third one is also 1 over 10. So at the end of the day, you multiply these three numbers together, 1/10 times 1/10 times 1/10. So you get 1 out of 1,000. So that is the probability. What about 666? And the answer is the same. 666 is just another combination of these three numbers. If you change this to any other combination, 789, 520, you name it, it's always the same answer, 1 out of 1,000. And finally, one day in April 1980, the daily lottery ticket number was 666. And then the next day, the newspaper reported that unusually large number of tickets for 66 has been purchased. And so people have spread rumors saying that the lottery has been fixed. And because part of people's concern was that all the three digits were the same. What is the probability that this would happen? Should we be surprised if we see a repeated digit number? So we would like to consider the probability. What is the probability of a repeat number, of three digits repeat? So here you draw this three digits, here, three digits. Digits repeat. Well, that consists of actually 10 elementary events. You can have 0, 0, 0, and plus 1, 1, 1, and all the way up to 999. Those are all the possible combinations. 999. So the probability of the first one is 1 out of 100 as we calculated. The second one is the same. And all the way up to the last one. So at the end of the day, the chances for you to see is actually 1 of 1,000. Sorry, 1 of 1,000, 1 of 1,000, 1 of 1,000. And you have 10 of those terms. So it's 10 over 1,000, which is about 1%, 1 over 100 or 1%. So is this likely to happen? The answer is not very likely, but it's not too surprising. Also, if you just keep doing this kind of lottery every day, in a year, you'll probably see 2, 3, 4, 5 times that happens. That's like 1% of the number of days. But if you do see it more often than that, like if you see it a couple of times per week, that may indicate a problem. Again, the chances of you seeing the repeated digits is 1 out of 100. All right, thank you for watching. I'll see you in the next video.